Bonjour à tous. Okay, so welcome to the last topic in the set of cheat sheets for the fundamental toolkit of chemistry. This topic is stoichiometry, which deals with the moles and basically a number of moles. And you need the number of moles to do almost everything in chemistry, quantitatively at least. So let's do some recap first from what you learned in O-levels, right? So some of the common mole calculations that you have encountered would be obviously how to calculate the number of moles. Another way that it can be phrased is what is the amount. So if the question is like, what is the amount of nitrogen in this mixture? They are asking you for the number of moles of nitrogen in that mixture. So there are two ways to do it. One way is the mass divided by the MR. And the other way is through the concentration, right? So volume times concentration will give you a number of moles. Now, the next one is the famous type for isotopes, right? Isotopes are atoms of the same element with a different number of neutrons, which gives rise to different mass, right? So to calculate the AR or the average AR, basically the ones that you see in your data booklet, the periodic table, you just take the sum of the percentages multiplied by the isotopic mass. So an example would be chlorine, right, which is 35.5. So why that is so is because chlorine has 25, oh, why is it not? 25%, 37 chlorine and 75% 35 chlorine. So if you take 25% times 37 plus 75% times 35, you will get something like 35.5, blah, 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 right? So percentage by mass would be the total mass of the element over the MR multiplied by 100%. So if like, say so what's the percentage by mass of sodium carbonate, of sodium in sodium carbonate, then you will take the mass of sodium. So the mass of sodium, so 2 times the mass of sodium divided by MR times 100%. Okay. So next would be percentage yield, which is the actual mass over the theoretical mass multiplied by 100%. So why this is important is because sometimes in the experiment, we don't always get all of what we thought we would get, right? Like for example, in say the synthesis of ethanoic acid, somehow you were supposed to get 5 grams, you calculated you would get 5 grams, but in actual fact, you only got 4 grams, right? So what is the percentage yield is 4 over 5 times 100. So you get a percentage yield of 80%. So using these numbers, you can sort of like estimate if you really wanted 5 grams, how much would you have needed, right? So you would take 5 divided by 80%, right? So 5 divided by 80% would be 6.25. So in actual fact, you will need 6.25 grams to accurately produce 5 grams of ethanoic acid. Okay, next is empirical formula. Empirical formula is the formula in the simplest ratio. So I use this format over here, and I use mass in 100 grams because it simplifies a lot of the calculations. And I think you should do it too, because the percentage composition will always remain the same, regardless of how many of the mass of that particular compound that you have used, right? Whether it's 1 gram, 5 grams, or 100 grams. So if it's 75% of it is this, then why not just use 75% of 100 grams, which is 75 grams, right? You don't need to think that much. Okay, and then this multiplication sign at the bottom is like, for example, sometimes when you get a mole ratio of 1.5:2, then what you would do is, right, like for example, if you do your calculations and you get like 1.5:2, what you do is you put times 2, and then you get 3:4. So your empirical formula is A3B4. Okay, now let's move on to titration. Titration is something that we should all be familiar with, you know, the burette and the pipette and the conical flask, and you turn, and then you measure, you record the volume, and then you do some calculations. So there are 3 main types of titrations being done in questions, right, or in the lab, right? So the first one is acid-base titration, which we should all be familiar with. So I give you a list over here, but it's not exhaustive. Just remember one for acids and one for bases. So for me, I like to remember for acids is methyl orange, and methyl orange turns red in an acid, and For bases, I like to remember thymo blue. Thymo blue turns blue in alkali, right? And then the endpoint is always like the mixture of the color. Because if you think about it, when you go from like say alkali to acid for methyl orange, you will go from yellow to red. And at that point when it becomes an acid, you will have like a bit of red. So yellow plus red is orange. So that's the endpoint. Okay, a famous question type is double indicator titration, right? Which, as the name suggests, you do titration twice for the same thing. And this is quite common for dibasic weak acids, right? Because dibasic weak acids have 2 protons, and yeah, basically. So in this case of carbonic acid H2CO3, you can convert the carbonate into a hydrogen carbonate first by adding 1 hydrogen at the proton, right, H plus. And then from here, you go from a base to something that's less basic. So you can use like phenolphthalein or thymo blue. In this case, I've used phenolphthalein because it goes from pink to colorless. And then in the next case, as you go from hydrogen carbonate to carbonic acid, you form an acid, right? So you can use methyl orange and you go from yellow to red. Of course, at the end point, it will be orange, right? But this is when it has been all converted, right? And you continue to add in excess. So the region over here should be red. Okay, next is back titration. Back titration is when you use a known excess of say like an acid and you react it with an unknown something. So there are a few main cases when you use this, right? So one is if say you have something that's insoluble, like for example, if you react acid with carbonate, right? Like say if you want to figure out how much carbonate is present inside a rock, right? And then you like add hydrochloric acid to that rock, and you add in excess so that you make sure that all of the carbonate has reacted already. So in this case, after you add the excess hydrochloric acid to the rock and then and dissolve / react all of the sodium carbonate or whatever carbonate is there, then you will take that final mixture, because that final mixture will contain all of the unreacted acid inside. Then you can use that unreacted acid to do titration. So to figure out how much was being reacted, so reacted would just be the excess that you added at the start minus away the unreacted that you determined via titration. Then you can use mole ratios to calculate the and work backwards to determine how much carbonate was present inside. Okay. Next is combustion. I give you a general formula here, but you don't have to memorize it. You can always just balance it on your own, right? So complete combustion, these equations for complete combustion, okay? Complete combustion produces carbon dioxide and water when you like burn a hydrocarbon in oxygen completely. Incomplete combustion is when you produce say carbon as soot or carbon monoxide. So this really depends. So you should read the question to figure out whether they want you to include both or just one of them, okay? So the order to balance this equation is carbon, hydrogen, and oxygen, which incidentally is in alphabetical order. Okay, next we would talk about redox reactions. So redox reactions is something that you have learned before, but a recap would be redox reactions occur, is a type of reaction where both reduction and oxidation occur. So the gold standard to determine whether it's reduction or oxidation is by looking at the changes in the oxidation state. And if you need a recap, it is over here. So I give you an example. Okay, so for Cr2O72 minus, the entire thing is -2. Oxygen is usually -2, so 7 times -2. And then you have 2 chromium, right? So you solve this equation for Cr, and you should get Cr equals to +6. Okay, so reduction is a reduction in the oxidation state, and oxidation is the increase in oxidation state. And because you have a decrease in oxidation state, it means that you gain electrons, right? Because electrons are negative, right? So when you decrease in number, you gain a negatively charged thing. And oxidation, because it's a gain in oxidation state, it is a loss of electrons. So this list over here is just a list of like common oxidation states that come out. You don't have to memorize it. You can always figure it out yourself, right? But the most important thing is balancing redox reactions. So what I like to do is this method called elephant on high chair. There are many ways to do it. One way is to look at half equations and then you balance, right? So half equations are in your data booklet. If they are not given, you can look at the data booklet. If not, you can just based on the question and then you figure it out yourself, right? So elephant or hydra works this way. First thing you do whenever you see a redox reaction is always to assign the oxidation state first, right? And then next, look at the relevant elements and balance them first. Then do it in this order of electrons, oxygen, hydrogen, and charge. So I'm going to go through how you can do this, right? It's already detailed over here, but I'm just going to draw it at the side so that we can see how this is done, right? Okay, so let's just say for this equation, right, we have Cr2O7 2 minus plus Fe2 plus becomes Cr3 plus Fe3 plus. Okay, so let's assign the oxidation states first. So Cr is plus 6, Fe is plus 2, and Cr is plus 3, and Fe is plus 3. So the relevant ions here are Cr, Fe, right? So if you look here on the left, Cr has 2, and on the right, there's only 1. So let's put a 2 there. Okay, next step. From Cr, so from plus 6 to plus 3, how many electrons do we gain? We gain 3 electrons per chromium. So in this case, we need to put 2 here. Okay, and then from plus 2 to plus 3, we lost how many electrons, right? So loss is the other way, right? So from 3 to 2 is 1 electron. So in this entire system, there must be the same number of electrons. So there are 6 here. So to balance this, we need to multiply this by 6. So let's add, let's use another color. So 6 here and 6 here. Next, after balancing the electrons, we need to balance the oxygen, right? So on the left-hand side, how many oxygens do we have? Okay, I'm running out of colors, but it's okay. Let's just continue using green. So on the left-hand side, we have 7 oxygens, but right-hand side, we don't have any. So we need to add 7 water. Okay, now we introduce hydrogens here, right? On the left-hand side, there's no hydrogen. Or there's no hydrogen, there's no hydrogen in the first place. But because we added water, now this equation must have hydrogen. So there are 14 hydrogens here. So let's add 14H plus. So that's H. Charges, we can check, right? So to check the number of, to check the charges, we have plus 14 here, and then minus 2, and plus 6 times 2, which is 12 plus 12 is 24. And then on the right now, we have 2 times 3 plus 6 times 3, which is 6 plus 18 is 24. So the charges are balanced. So we have balanced the equation already. But this is in acidic medium. If we want to make it in basic medium, all we need to do is convert all of the acidic things into water. So if you have 14H plus, we add 14OH minus, and because this is an equation, we must add it on both sides. This side, okay? So 14OH minus 14H plus, this will become what? 14H2O, right? Okay, and then on the right hand side, we have 7H2O. So we can simplify this. So your final equation for basic would be 7H2O plus Cr2O7 2 minus plus 6Fe2 plus forms 14OH minus plus 2Cr3 plus 6Fe3 plus. So with some practice, you should be able to do this within 30 seconds. And if you join as a member, I will be giving some questions. Or when I finalize the worksheets, you can buy the worksheets. Okay. And this is the last video in this series of for Fundamental Toolkit of Chemistry. If you like the videos, please consider supporting the channel. And you can always get a copy of this set of cheat sheets on your own. So as usual, like, share, comment, whatever on the coffee shop here, Instagram. And see you in another summary video. Bye-bye.